So last week we were talking about logic functions, Boolean algebra, Boolean functions, how to simplify using Boolean algebra, simple rules. We talked about truth tables, we talked about sum of products, product of sums. We also know how to write function given a truth table, how to simplify it using Boolean algebra, and we also took some examples and did it. One problem I said in Boolean algebra was that you don't know how much simplification is possible, because we took examples that are very simple, so we were able to get to the minimum. But when the function is big, many variables and many terms, how to apply Boolean algebra and how you know that we have simplified enough and it is not possible to simplify anymore is difficult. So I said we have systematic methods of doing it. There are many methods today with all these computers and all that. There are computer based methods. That is what's used in today's design. In today's design, we use computer based methods. But between the Boolean algebra and the computer based method, there is something called map method. I will explain that to you today. Map method of Boolean simplification or Boolean reduction. This based on a very simple Boolean algebra rule, which is a plus a bar is 1 or x plus x bar is 1. We will take the same truth table we did the other day. A, B, C are 3 variables, F is the output, there are 8 rows corresponding to all combinations of inputs. And this is the function we did the other day. F is 1, 1, 0, 1, 1, 0, 0, 0. We wrote F is A bar, B bar, C bar, or A bar, B bar, C, or A bar, B, C, or A, B bar, C bar. And then we try to simplify it and wrote the final equation as A, B bar, A bar, C plus B bar, C bar. Today I will get the same thing using another method called map method. The map method is given a name Karnaugh map based on the person who suggested this method, Karnaugh map, K map they call it sometimes. What you do is you make it into a graph. How many terms are there? There are 8 terms. So you divide this into 8 cells. Now each of these cell corresponds to one of the terms. How do you know that? So we put here A, B, C here. A0, A is 1. A0 corresponds to first 4 rows. A0 corresponds to second 4 rows. Within the first row, first 4 rows, this is B bar, C bar, B bar C bar, that is B bar C, then that is B C bar. I will write here B C bar, not here, and then B C. So this is A bar B bar C bar, A bar B bar C, A bar B C bar, A bar B C. Likewise with A, this is A B bar C bar, A B bar C, A B C bar, A B C. So these 8 rows, whenever there is a 1 on the output, you put a 1 here. Whenever there is a 0 output, you put a 0 here. In other words, this is mapping of the truth table. This is truth table, I told you. The truth table is a table in which all the possible inputs appear and the corresponding outputs appear. This is called tabulation. This is the same as the tabulation in a map form, 2-dimensional map. Now, what is the advantage? Because we have this rule A plus A bar is 1, you will find here in this map one peculiar property, very interesting property. 2 adjacent cells, if each a cell or square, whatever you want to call it, between 2 adjacent squares or 2 adjacent cells, only one variable is different. For example, A bar is common to all the 4. Here it is B C bar, B bar C bar, this is B C. So this is between this and this, C is 0 here, C is 1 here. Between this and this, B is 0, B is 1, C is 1. Between this and this, B is 1, C is 1 here, C is 0 here. So 2 neighboring cells or adjacent cells differ in only one variable, and if you have 1 in both of them, suppose I have 1 in both of them, this corresponds to A bar, B bar, C bar, A bar, B bar, C. Now C bar and C are, so this is combined as A bar, B bar. This is what I said. Only one rule I am applying repeatedly. Boolean algebra, the simplest rule of Boolean algebra is A plus A bar is 1 or B plus B bar is 1, whatever. That rule is repeatedly applied, so that means now I can make these 2 cells, combine them, this has 3 variables, this has 3 variables, out of which one variable is different from here and here, that variable gets eliminated, knocked off. So I can look at this and say, without all these equations, I can look and say A bar, B bar, this is what it is. Now between this and this, A bar, B bar, C, A bar, B, C. So A is A bar, so between these 2, I have A bar, B gets eliminated because this is B bar here, B here, C. And again these 2. A is 0, A is 1, B bar, C bar. So between these 2, this is B bar, C bar. Now there are 3 groups of 1s. They should be power of 2. You can group 2 1s, 4 1s, 8 1s, 16 1s like that, and the property should be that variables should remain constant, rest of the variables get knocked off. Whichever variable does not change will be available, will be appearing in the final result. So this is now A bar B bar, A bar B bar or A bar C, B bar C bar. This is my F. Again, I have combined this one along with this, along with this. This one goes with this and this. So I could have simply done it differently. I could have done it this way. Two ones are enough, two groups. This is unnecessary now because this one appears in this and this. This one appears in this and this. There is no need. Every one should be at least covered once. But covering a one more than one does not matter. It is not a mistake. But putting this repeated coverage will result in number of terms being increased. We do not want that. We want to have as few terms as possible, as few terms as required. So even though I do like that, I should have done this way. Corresponds to, this corresponds to A bar C. This corresponds to B bar C bar. So that means my F is B bar C bar or A bar C. If you draw this, all the four terms of this, A bar B bar C bar, A bar B C bar, A bar B bar C, A bar B C, A B bar C bar, if you write all of them and simplify using Boolean algebra, you will get the same result. This is a very quick, efficient method called map method or Karnaugh map method. The idea is have as few groups as possible, at the same time not leave out any one. All the ones in the map should be covered at least once. Covering a one more than one is not a problem, it is not a mistake. But if you unnecessarily keep on covering a one repeatedly like this, will increase the number of terms. We do not want that. In this case I could have done it easily this. I did not want to do it in the beginning, I wanted to show you this way and then this way. Now this is same as this. Here I have only two terms, here I have three terms. So naturally this is more efficient. So if I now want to combine, make this, I can draw a circuit with B bar C bar, A bar C, I use two AND gates, one OR gate, three inverters, two input AND, one 2 input OR, three inverters. If I did not do the simplification, I would have used four 3 input AND gates, one 4 input OR gate and three inverters. This is called map method or Karnaugh map method. Systematically it reduces the function. You don't have to worry whether you have reached the minimum or not. As long as you cover all the ones in the simplest possible way without overlapping. Overlapping is not a mistake. If that is it has to be done, you can do it. Sometimes I will give an example where I have to do it more than once, but you do not do it unnecessarily. Once you have covered a one, there is no need to cover it again. Sometimes it becomes necessary to cover it. This is what is known as the map method, Karnaugh map method, with 3 variables. If it's 4 variables, you will have 16 cells, because 4 variables will have 16 rows, 5 variables 32 rows, 2 variables 4 rows. So I can do a 2 variable map, 3 variable map, 4 variable map, 5 variable map, 6 variable map, and so on. This is an efficient method, but the number of variables is too large, we can't do this. Boolean algebra is difficult, number of variables being too large. You start writing the functions, start applying Boolean algebra, you don't know how long, how much you can do it. So in between you have this method, and even these files, that is the number of variables is too large, you go for computerized reduction. That is what they do today's technology in designing of big digital circuits. They don't use Karnaugh maps, they use computerized reduction. We are not going to talk about that computer reduction, I will tell you the names of that, but it is all automatic, there are tools. You feed all the terms along with the inputs and the outputs, and then it does a reduction and gives you the result. That is not necessary to know because a computer does it. This is an intermediate method which is very useful if you are going to do a simple circuit, design a circuit with some variables, a few outputs. The map method or the Karnaugh map method is the best one. I will give you one more example. Supposing I have F is, see one more thing is I do not have to write this truth table every time. I told you these are called min terms, if you remember the other day. If the output is 1, it's called a min term, if the output is 0, it's called a max term. So which are the min terms which are 1? If I list them out, you know, for example, this is 0, this is term 0, term 1, M0, M1, M2, M3, M4, M5, M6, M7. With 3 variables, we will have 8 terms starting with 0 to 7. 4 variables will have 16 terms starting with 0 to 15. So all I have to tell you is which terms are 1s and which terms are 0. So for example, I can now say M0, M1, M3, M4. If I say that, you know immediately this is what it is. So now I will give you an example like that. There are 3 variables or 4 variables or 3 variables make it. M0, M1, M3, M5. These are 3 variables, which means it is the first term of the this is 1, this is 3 because this is 0. You don't have to write it every time, we know it all. M1, M3 and M5, all the rest are zeros. If I say this, this is understood. The whole truth table, making zeros and ones, all that is not required. Now, If that is the case, how do I map it? I map it like this. This is 0, 1, 2, 3, 4, 5, 6, 7. Now 1, 3, 5. 1, 3, 5. These are ones. Rest of them are zeros. Zero you don't have to write. I am just showing it to you, but don't clutter the map. Don't clutter the map like this. This is enough. Now how do you simplify it? This is A bar C. This is B bar C. This is where I am telling you that more than once covering is required. There are only 3 terms. If I do it this way, I have covered these 2 ones. Now these 2 ones I cover it this way, I get 2 terms. If I do not do this, if I do not do this, I could have covered this way. Supposing I don't do this way. I have already covered this one and this one. This one is uncovered. I have to cover all the ones. Only then it's simplified. Now supposing I do not cover this way, I cover this way. This is also right, but this will have 3 terms. This is A, B bar, C. But we want, if we cover this way, it comes B bar C. So this will be simpler than this. This is a 2 input AND gate, this is a 3 input AND gate. So why should I cover it this way when I can cover it this way? So the rule is cover all the ones at least once. You can cover more than once, any one, provided it simplifies your final expression. This is a typical example. If I use these 2, this term will come. If I use this term alone, this will come. But if I also do this, now this one gets covered both in this and this, that is not a mistake. But I should not leave anything out. I should cover all the ones. But do not unnecessarily do it. In this case, I have already done this, then there is no point in doing it. Because this has resulted in 2 inputs, 2 input gate, this has resulted in 2 input gate, we have covered everything, whereas doing this extra is going to increase the number of terms which I don't want. So do not unnecessarily do it. So the rule is cover all the ones. If necessary to reduce the function, any one can be covered more than once. But if you have covered all the ones and you got the minimum expression, do not unnecessarily go and cover more time. That is not required. This is a simple rule. Now, one other thing I want to tell you before I move on. I have 7 min terms, 0 to 7, 8 min terms. 0, 1, 2, 3. I did not write 0, 1, 2, 3, 4, 5, 6, 7. I wrote 0, 1, 2, 3, 4, 5, 6, 7. The reason is I want 2 cells to be adjacent. Only one term should be different. If I take this as 1, 0 and this as 1, 1, this is 0, 1, this is 1 0. Here B is 0, C is 1, here B is 1, C is 0. Both B and C are different. I want only one term to be different from one cell to the next cell. Only then I can use this A plus A bar. I can use this A plus A bar is equal to 1 formula. Only if I have two terms who differ in only one variable. If two terms differ in more than one variable, I cannot use this. That is the reason I go here 0 1 1 1, so that between this and this only one variable change. This is B 0, C is 1, B is 1, C is 1. Between this and this, B is 1, C is 1, C is 0. Two adjacent terms, two adjacent cells, two adjacent squares, whatever you want to call them, can differ only in one variable. That way I have one more interesting result. This and this are also adjacent. This is 0 0, this is 1 0, only one variable change. This end and that end are together. I can combine them. Suppose I had a 1 here and a 1 here, I can combine them. Suppose I had a 1 here and 1 here, I can combine them. So two corners, four corners. So I will give you an example now. Any questions now? Any questions? Okay, let me give you one more example. I will give you an example of sigma f is equal to, instead of writing m0 plus m1 plus, what I do is summation notation, like arithmetics. Like in arithmetic we do summation, or algebra we do summation. So you write summation 1, 3, 4, 5, 7, 10, 11. This is what we typically use. Very simple to understand. This is 4 variables because up to 15 is there. If you want to be explicit, you write here ABCD is a function. 15, 0 to 15, 16 minterms are possible, out of which the following minterms 1, 3, 4, 5, 7, 10, 11 are 1s, all other minterms are zeros. So I don't have to write the truth table A, B, C, D, F, 0, 0, 0, 0, 0, all that I don't have to write. So I now directly go for the K map. 16 cells must be there because there are 4 variables. AB here, CD here, 0, 0, 0, 1. Again with the same rule, 1, 0, 1, 1. This and this are adjacent, this and this is adjacent. Now this and this is adjacent. This is 0, 0, 1, 0, only one variable change. Similarly, this is 0, 0, 0, 1, 1, 1, 1, 0. This is adjacent to this is adjacent to this is adjacent to this. Now, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What are the variable terms for which it is 1 now? M1 is 1, M3 is 1, M4 is 1, M5 is 1, M7 is 1, M10 is 1, M11 is 1. All others are zeros. 1, 3, 4, 5, 7, 10, 11. Now, as many ones as possible you should group. 2 ones, 4 ones, 8 ones. Larger the group, smaller is the term. 2 terms together only will reduce 1 variable. 4 ones together will reduce 2 variables. 8 ones together will reduce 3 variables. 16 ones together will reduce 4 variables. So, more number of variables reduced is better for us. Hardware will be simpler, logic will be simpler, we save hardware cost and money. So, I am going to use all these 4 ones. 1, 1, this is adjacent, this is adjacent to this, 0, 1, this is 0, 1, 1, 1, 0, 0, 0, 1. So, all these 4 are adjacent. These 2 are adjacent. This one is isolated. I do not want to keep it as an isolated, I can combine this. So, I want to call this 1, term 1, term 2, term 3. There are 3 terms, term 1, term 2, term 3. They are called prime implicants. Group of ones together called a prime implicant. Now, this prime implicant will have A bar here common, B changes, D remains common, C changes. So, this is A bar D. So, 1 is A bar D. Four terms, 2 variables. This number 2 prime implicant this is CD, this is CD bar. So, D bar D goes because this is D bar and this is AB bar. So, this will be AB bar C. 2 terms, so 3 variables. This one alone can be written as 1 because I would have covered all the ones. If you take this one by itself isolated, I will have a 4 variable term because 1 only can give you 4 variable term, 2 ones will give you 3 variable terms, 4 ones will give you 2 variable term and so forth. So, this one, but I can combine this. So, this is essential, I have to put this one because otherwise this one gets left out, isolated. I can't afford to do that. I have to take this one into account, but I do not have to have it separately because it can also combine with this. That is what I said. Cover all the ones, but there is no need only one, every one should be covered once. If covering one more ones, more than once, is going to simplify the term, then you do it. So, now this should be A bar B C bar. A bar B C bar. So, now F is A bar D, A B bar C, this is the total function. I can realize it using 3 gates. This is A bar D, this is A bar, A, B bar, C bar, A, B bar, C, A bar, B, C. A bar, B, C bar. All of them combined into an OR term. This is A bar, E, first term. This is second term, A, B bar, C. This is the third term, bar, B, C bar. All of them combined using OR gate will give you the final function F. This is a very systematic, elegant method of simplification of Boolean functions or truth tables. I have shown with 2 variables, I have shown with 3 variables, 4, I'm sorry, I have showed with 3 variables, I have showed with 4 variables. 5 variables, 32 cells will be there. 32 cells is very difficult to draw a map. So you do it 2 maps, 16, 16, and then in one you make A is equal to 0, the other one you make A is equal to 1. 32 variable you want, 4 maps, each 8, each 16, 64, A, B, C, D, E, F, like that. Beyond that, they don't do this. This map method is elegant, easy to follow, quick results, but the number of variables should not be very large. So we have Boolean algebra on one side. We have to remember all the Boolean algebra rules and try to understand properly, apply it. You should know what to apply, it should strike you. Correct rule. If it does not strike you, no way you can reach the minimum. So, and also once you apply Boolean algebra, you don't know whether it is minimum or you can apply still more. On the other hand, the computerized methods, large number of variables, you give the truth table in some form, gives the reduction and it also gives the hardware. That is what is done in today's digital design. Large circuits are involved. In between is the Karnaugh Map Method, up to 4, 5 variables, 6 variables. Systematic way of reducing. Draw a 2-dimensional map, put ones wherever f is 1, leave the rest as zeros, combine the ones, make sure that ones are combined with 2, 4 or 6, 2, 4, 8 like that. Make sure all the ones are covered. At the same time you can cover more than once provided it is going to reduce in the final expression. Now everything as I told you is a prime implicant. There are 3 prime implicants. This one, 1, 2 and 3, these are prime implicant. A bar D is a prime implicant. A, B bar C, prime implicant. 2, prime implicant 3 is A bar B, C bar. Out of these 3 prime implicants, all of them are essential. If I do not have this, this and this will not get covered. My job is to cover all the ones. Make sure all the ones are covered, taken into account. These 3 are required, this one. These 2 are also essential. Without this second prime implicant, these 2 ones get left out. This is also essential because without this one gets left out. So a prime implicant is called essential prime implicant. If at least one is unique to that. At least one should be in a group which is not covered anywhere else. So, in this case, this is essential because these two ones are required. This is essential because these three are required. This is essential because this one gets left out otherwise. So, all the three prime implicants are called essential prime implicants. Sometimes we will have two ways of combining and both of them are not essential, they are called non-essential. The earlier example, if you remember, this one, where was that? We had earlier this was required, this was required, this one we put. This is essential because this one gets left out if I do not have this. This, so I will call this 1, 2, 3. 1 is essential because this one gets left out otherwise. 2 is essential because this one gets left out otherwise. 3 is non-essential because these two ones have already been combined in some other way. So, the final F would be sum of all essential prime implicants plus as many non-essential prime implicants which are required to combine all the ones satisfactorily. I did not write that part. Non-essential pairs which are required to complete the map. In essential prime implicant has to be in the final expression. Non-essential prime implicant need not be, but it is also required sometimes because otherwise that one gets left out. I will give you one more example, I will give you a couple of minutes, see whether you can do it yourself, very simple exercise. One more example. A, B, C, D is not necessary. You can also say X, Y, W, X, Y, Z. Is sigma M in terms 0, 2, 5, 8, 9, 10, 11, oh. This is one example. I will give you a couple of minutes to see if you can do it yourself, otherwise I will do it. Very easy. If somebody has finished it, raise your hand.
Hello, sir.
Yes?
Sir, Subhashish has an answer. He would like to
Yes.
speak to you.
Tell me.
A bar,
A bar,
sir, A bar, B bar, A bar, B bar, D bar,
A bar, B bar, D bar,
plus
A
plus
plus
A bar, C bar, D.
A bar, C bar, D. Huh?
Yes, sir.
Let me see. So right or not? Good. I hope it is right. Oh.
Sir, the last term will be B, C bar, D.
B, C bar, D. Okay. Okay?
Yes, sir.
Let me try. 0, 2, 5, 8, 9, 10, 11. So this is one big group, EPI. You called A, I call it W, that doesn't matter. Okay? I got W, X, Y, Z. Because W is 1, X changes, Y changes, Z changes. So this is W or A. You called it A, I call it W. Doesn't matter. Good. Then this one. That is
Yes, sir.
X bar X, the Y bar Z.
Yes, sir.
Good.
B, C bar, D.
Yeah, the same as this. This one is right. Oh, this is X, A, B bar, D. Is that what you meant? This one?
Sir, that one is sir, B, C bar, D.
B, C bar, D.
Sir, X is B.
Yeah, yeah, X
Sir,
is
W
B,
is
right.
A.
Right. B, C bar, D, correct. And then this
Yes,
one
sir.
is, this one and this one will go together because they are adjacent. That will be
Uh,
X bar, Y bar, Z.
Sir, we can combine them together, that four
Wait a minute,
ones
wait a
at
minute.
the corners.
Oh, you are right, man. Right? These four ones will make X bar, Z bar, which is equal to, according to you, Y bar, B bar, D bar. So this
Yes,
can
sir.
knock off.
Mhm.
Good. Very good.
Thank you, sir.
Very nice. So simple, man, this course. All of you can get 100 out of 100. I am going to make one minor change in this. If you remember, the other day I told you, when you have a truth table with more ones than zeros, we have fewer ones and more zeros, use min terms and combine them and simplify it. On the other hand, if there are lots of ones and fewer zeros, you can combine the max terms and simplify it. I told you that, if you remember. Let me see if I can do that here. I will redraw it. It has become a little messy. Same thing I am going to draw with zeros instead of ones. I am going to in order to please him, I am going to use ABCD because he was using ABCD. I will use ABCD also. Now this was a 0, 0, 0, 0, 0, all of them ones. See, wherever 1 was there I left it, wherever there is no 1 I put a 0, 0, 0, 0, 0, 0. So there are only 5 zeros, whereas there are 11 ones, 1, 2, 3 plus 8, 11 ones. 11 ones, I have to do it this way. There are 5 zeros. So how do I do this? Using max terms. There are 2 ways of doing it. You can write f bar. If you write f bar will be, the other day I showed you all this, De Morgan's and all that. F bar would be A bar, B bar, D. That is this. Then it should be A bar, B, C. And this is separate one. I can't combine this with anyone. This would be A bar, B, C bar, D bar. F bar. So I can apply De Morgan's. Yes? Yeah, please tell. Karnaugh, here somebody has to say something. Mr. Karnaugh? Unmute him.
One second, sir. 1 second, sir.
Okay. You want to say something?
Yes, sir. 1 moment. 1 second, sir.
Yes, no problem.
Yeah, go ahead. Who was that, please?
Yes.
Sir Subhashish.
Yeah,
Subhashish. Oh, 1 moment. 1 moment, Subhashish.
Yes, sir.
Yeah, go ahead. You can ask the question.
Sir, that 00, CD 00 and 10 we can combine, sir.
What? Oh! There you go, man.
CD00 and 10.
Yes, sir. Like this, right?
Yes, sir.
There you go. I think you are becoming better than me.
No,
Huh?
sir, you are always better than me, sir. Sir, I saw your NPTEL lectures. From that only I have learned all this.
Okay. Anyway, next class you are teaching, I am listening. Okay?
No, sir, you will only teach.
A bar B A bar B D bar, right? Same as this.
Yes, sir.
3 terms there, 3 terms here. Now we can do De Morgan's, get F, or this is sum of products. Using zeros we put F bar, apply De Morgan's, get F, simplify it. I can directly get F by putting this F as using max terms. Now I will use max terms. This will be A or B or D bar. And A, B bar and A and A or B bar or C bar or and A, B, D bar. Wait a minute. A, B bar, A, B bar and D or D. Remember I told you this rule. A variable in the min term becomes its invert in the max term, and sign becomes or sign becomes and sign. So I take each of these, instead of I would have written it as A bar, B bar, D, instead now I write A, B and D bar, and I will put a R in between. Then instead of or here, I will put an and here and use this as A, B bar, C bar. This one will be A, B bar, D. Now I can simplify this and get that form. You see, I can simplify this using De Morgan's and get this expression, or I can simplify this expression and get that form. But this is not very popular. Reason is we normally use AND gates followed by OR gates. This is called AND OR invert form. AND OR invert gates. This will become OR and invert. There is no incentive to do this unless you have some reason to do it. Suppose you have lot of OR gates of different inputs and fewer number of AND gates. I would like to have OR gates followed by AND gates and inverter. This is called, so normal tendency would be to use this form and or invert, simplify it. But why do you have to do this? Because there are fewer zeros. So there are now two ways. Put all ones, get the expression. It's also simple, only 3 terms, not a big deal. All simplified it using 3 functions, 3 terms using AND or invert. Or you can use zeros and get F bar and do the simplification. If occasionally for any reason you are asked do or followed by AND followed by or and followed by AND, then you go for this form. But we have shown in the last class using truth table, all are equivalent. We took an example, we did its AND form, we did OR form, we did De Morgan's, we did without De Morgan's. In other words, it is all very simple. Whole thing is very simple. So one more example and we will stop here. Use AND or invert form. Last example for today. And I will give you the homework. Using lots of this. I don't have to give you homework. Any book you are following will have lots and lots of problems on Karnaugh map simplification. You take Mano, you take Roth, you take Tossi, T-O-C-C-I, Tossi. Whatever book you take, this chapter, simplification using Karnaugh maps, is very, very favorite chapter for all the authors. So I am sure we will have lots of problems. I will also give you an example, exercise. I will give you a homework problem set soon, but now you do it. Pi of m suppose you are given like that, 4 variables again. Four variable function f, product, that means I have to use max terms, which means my function will be zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, this is what it is. Now I have used max terms, so I will tell you where are the zeros instead of ones. You map zeros, you have 2 choices, using zeros and directly get the expression, or use ones wherever there is no zero, use a min term expression. Either way it is same. I will prefer this min term. I am going to use min terms and do it. These 4 ones. There is one term 1, prime implicant 1. Prime implicant 2. These 4 are adjacent, these 2 and these 2. So this is prime implicant 2. Prime implicant 3. Everything is an essential prime implicant because these ones get covered in this one gets covered in this one, and this one gets left out. So all of them are essential prime implicant EPIs. Term 1 is all corners, B bar, D bar. All corners, B bar, D bar. Second one is this, A, D bar. Third one is A, B, C. Fourth one is A bar, B bar, C bar. Any doubts? Any questions? So today we made very good progress. Simplification using Karnaugh maps, very simple topic. Something like playing a game, like tic-tac-toe, you know, have you played? Put like this, into, and then cross and all that, something like that. It's a nice game, we should play this very often. Only one thing about this is, we will only get an AND OR invert, or OR AND invert. Other gates like AND gate, NAND gate, NOR gates, exclusive OR we don't use. So next class, I will take some of these functions and reduce them using NAND gates. Because sometimes they will tell you, simplify this function, but use only NAND gates. So what do? You first simplify it using Karnaugh map, and then try to see how to change that into an OR gate or NAND gate or NOR gate. That is essential because, as I told you, these NAND and NOR are called what? Universal gates.
Universal gates.
So universal gate is required. Your boss has stocked 10,000 NAND gates, and whatever design he wants you to do, he wants you to use only NAND gates. So he gives you a function ABCD, you simplify it using Karnaugh map, but then you come with an AND OR invert solution. He says no, I want only NAND gates. How will you do that? We will see it next class. And meanwhile, as I said, please practice this. It's a very simple topic. All books have lots of problems. I will also give you problems, but I don't know when. I have to ask my TAs, teaching assistants, to come up with a sheet, but I will tell you that very soon. But you can also practice. Next class we will talk about NAND gates, NOR gates, implementation of same logic functions. You can take any one of these. I can take this and say how to get NAND equivalent or not equivalent. Okay then, have a nice week, evening. If you have any questions, you can ask me now. You can unmute Mr. Kannan. Any questions?
I have unmuted everyone, sir.
Yeah. Any questions? No questions? Okay, good. Have a nice pleasant evening.